Welcome to Ask and Learn.
We're asked to construct a deterministic finite-state automaton that recognizes the set of all bit strings that contain an even number of zeros and an odd number of ones. So let S be the set of all bit strings with an even number of zeros and an odd number of ones. And let S0 be a start state. Now consider the empty string. We see that the empty string does not have an odd number of ones, even though it has an even number of zeros, so it won't be in the set S. And therefore, S0 will not be a final state. And let's consider 4 states total. So we have S0 represents that there were an even number of zeros and an even number of ones. In the previous bits, if there were any bits yet, S1 represents there were an even number of zeros and an odd number of ones in the previous bits. And because this is exactly the description of S, it follows that S1 is going to be a final state. S2 represents there are an odd number of zeros and an even number of ones in the previous bits. Clearly, this is not a final state. And finally, S3 represents that there were an odd number of zeros and an odd number of ones in the previous bits, which is also clearly not a final state. Now let's consider the transitions between states. So, starting at state S0, suppose the input is 1 at S0. Then we're going to move from S0. So the total number of ones was originally even, but since we're adding one, the total number of ones is now odd. The number of zeros is still even, so we're going to move to state S1. Now, let's suppose that the input is 0 at S0. We have that the total number of zeros is now odd. Total number of ones is still even, so we're going to move from S0 to S3, or sorry, S2. Now, suppose that we have an input of 1 at S1. Then we see that the total number of zeros is remaining the same. So we still have an odd number or an even number of zeros, but the number of ones is now odd. And so we're going to move from S1 to S0. Sorry, the number of ones was odd. Now it becomes even. So now I have an even number of zeros and ones. So I'll move to S0. And likewise, suppose that the input is 0 at S1. Then we're going to move to S3 from S1 because the number of zeros was originally even and now it has become odd while the number of ones remains odd. And let's suppose that the input is 1 at S2. Well, then we're going to move from S2 to S3 because since we're at S2, the number of zeros is remaining the same, so we still have a odd number of zeros, and the number of ones was originally even, but now has become odd. And suppose that we have an input of 0 at S2. So the number of zeros originally was odd, but now it is becoming even, and the number of ones remains even. So we're going to move from S2 to S0. Suppose that the input is 1 at S3. At S3 we have that there are an odd number of zeros and an odd number of ones. So this changes to an odd number of zeros and an even number of ones. And so we're going to move from S3 to S2. And now let's suppose that the input is 0 at S3. Well, we originally had an odd number of zeros and odd numbers of ones, so this changes to an even number of zeros and an odd number of ones, which is S1. So we're going to move from S3 to the final state, S1.